Good afternoon. Can you hear me? Loud enough? Okay, the last time we had a chem quiz, and it was a bonus quiz. That was question, if I recall, 22 in your midterm, and I have to correct myself, or we have to correct ourselves. The answer was actually that there are two dipolar structures, and with this the answer was 2 and not 1. But in reality, actually, the answer is 1. But according to your rules, the answer is 2. Okay, there's 2 dipolar structures. So everyone who voted for 1 will get the extra point, and everyone who voted for 2 will get the extra point. Okay, and also in the midterm, those who had said 1 gets it right, it gets 3 points, and those who said 2 get these 3 points. Okay, it's raining points on you, isn't it? Okay, alrighty. With this good news, we're going to review what we did the last time. The last time we talked about. Can I have it a tiny little bit louder? The last time we talked about. I have to talk above you, okay? The last time we talked about real gases, and real gases, they have actually a volume, the atoms, okay? And real gases have these intermolecular forces or interatomic forces that they attract each other. These forces, I have explained those, these are dipole forces and induced dipole forces. These forces, however, are relatively small compared to, and can be broken easily if these particles have very high kinetic energy. If you have very high kinetic energy, then these forces are not active. They are not enacted by the gases. And with this, you have an ideal behavior again. And when we know that the temperature is directly of an ideal gas, or of any gas, is directly proportional to the energy, or vice versa. So it's we have RT. And with this, you know, if you have a high temperature, then these interactive forces cannot enact on each other, and you have ideal behavior again. And we call this temperature the critical temperature, and this was here above the critical temperature. Even real gases behave like ideal gases, okay? There's no interaction between the particles, and once you have a gas, a real gas above the critical temperature, you just deal with it like an ideal gas. We have also seen that we correct the P times V is N times R times T gas equation. We have to adjust it for the collisions and attractions, so the pressure has to be adjusted, and the volume has to be adjusted because you have finite volumes. That means that molecules and atoms have a volume, and with this you get some correction factors, A and B, A for the pressure and B for the volume, and N you're familiar with is the number of moles, and V is the volume, and here the same number of moles. And you see these correction factors are not very large for helium, for example. Helium, if the interaction is not very large, so you have a very low boiling point for helium, for example. Hydrogen has quite a bit of interaction because you have hydrogen bonds. So we have talked about phase diagrams, and we have talked about CO2. And the phase diagram is a depiction or a plot of P versus the temperature. And so you see there are different phases. Of course, you have water. Water can be ice, or liquid water, or steam. So you have 3 phases. In water, we come to water especially in particular, because water is very special for all of us. Without water, nothing would happen for us. We wouldn't be here, especially our bodies, because 70% is water. Okay, I hope it's not up here; it's somewhere else. Okay, and so with carbon dioxide, you have seen that at certain temperatures and pressures, carbon dioxide can go directly from the solid to the gas phase. You see, the pressure was relatively low; it was atmospheric pressure, and it had this piece of carbon dioxide, frozen solid carbon dioxide. That's the solid phase, and it evaporated straight into the gas phase. It didn't go through the liquid phase. And with this, we are here. We go from these are the phase boundaries here. This is the boundary between the solid phase here and the gas phase here. And we were at this pressure here. The temperature was room temperature, so we let it warm up, and it formed. Suddenly, it was gas. So there was no liquid in there. Of course, when we go higher in pressure, if we put more pressure on it, then the solid goes to the liquid. Here, for example, the solid goes to the liquid, and then the liquid goes to the gas. If we increase the pressure, you see that? And so we go from the solid to the liquid here, from the solid to the gas here, from the gas to the liquid here, and from the liquid to the gas here. So how do I go from the liquid to the gas? All I have to do is decrease and increase the pressure. I go from the liquid to the gas at a certain temperature. Now we have here a point, and this is called the triple point. Obviously, the solid, the liquid, and the gas are at this point coexistent. So they are at the same time existing, and there's a certain, this is the temperature for the triple point, is minus 56.6 degrees Celsius and 5.1 atmospheres of pressure. So we should be able to make an experiment where we put CO2 somewhere under pressure and let it heat up, and then we should see the solid, the liquid, and the gas phase at the same time. It's not an easy experiment, but Karen has made it quite easy. She worked on this. Let's see, this is the phase from the liquid to the gas here. This is from the solid to the gas, that's sublimation, and this would be from the liquid to the solid. What would this be called? Freezing, okay, for CO2. That's how the liquid CO2 becomes solid. And so let's look at the triple point of CO2. You never have seen 3 phases together. You can see maybe water boiling. This is a gas phase and the liquid phase, but you can't do 3 phases together. Let's do that now. So let me explain to you a little bit what you see here. So far we don't see much. Maybe we need a light or whatever. You're the director. I'm sorry. I stay out of this. Okay. So there's a little bit of glare here. So this is a glass tube here. Okay. This is a glass tube, and we have around here we have a container. This glass tube is closed here. Maybe we can use the data camera for now for a second. Okay, so you see that glass tube here? Okay, and there we have a cylinder around this which we flush with helium, because when there's air on the outside, the air is outside here, the air can get in here, not in here, of course. And so we flush this out with helium, that when it condenses, the air starts to condense and freeze. That way you can see it. So we flush this with helium, that's why you have these in and out hoses there. And so now Karen, maybe can you have the other shot again? Karen will fill this now with CO2, and this is dry ice, CO2. And now Karen will close this up here with a valve and a pressure gauge, and unfortunately we don't want to see the pressure gauge, because here's the pressure gauge, okay? She will close this, and now what should happen? This thing here will starting to melt, and then there's the pressure going up. You see that? The pressure gauge is on top here. This is closed, completely closed. And now you see, the pressure is going up and up and up and up and up and up. And so you have here, there's some change already happening. The pressure goes further up. And you see there's some structure. It's afraid of me. See that? Oh, it's melting. And so now there should be a liquid coming up. That's still the solid. And there's got to be a liquid on top of it. There it comes. Can we see the other picture now? You see the liquid? So far it's not boiling. It will start boiling. And when it boils, it will produce gas. It goes into space. It's liquid, it's gases, so you have the solid here. The liquid so far, it's not boiling, but eventually it will start boiling when the pressure gets up to the right pressure. What's the pressure? What does the gauge say? 96. Is it still going up? There, it's boiling. You see it boiling? So the gas goes in here. This is the gas phase here. This is the liquid, and this is the solid. Isn't that marvelous? Oh. you see it in Chem 1A. Not everybody can show you that because they didn't have such an ingenious apparatus that Karen did here. We used to have a very hard time. We used to heat it, and it was very dangerous actually. And so this is much better. You see, boiling carbon dioxide and solid carbon dioxide. The gas, of course, I can show you because gas is colorless. But if it boils, it's got to go somewhere. Okay. All right. So is the pressure? What happens to the pressure now? It's holding steady. So we have the triple point, and the pressure we see, it would be, of course, our manometer is not. It would be 5.1 atmosphere. That's the pressure that you see there. What does the manometer say? What does the manometer say? 96, so it's not in atmospheres, obviously. No, it's in PSI. So you can calculate this at home then, how much is 96 PSI in atmosphere. Okay, so there you go. See that pressure? There's, of course, there's a relief valve in it. The whole thing doesn't fly around our ears, you know. Okay, good. That's good. Karen, thank you very much. You see that at Chem 1A. Isn't that exciting? And so now we were at this point. And you see the solid between the liquid, the line, has a positive slope, slopes to the right. Nearly all material that has a phase diagram has a positive slope, except one, the most important one for us. This is water. It has a negative slope. Okay, so now that means if I am here at I have a solid, and I increase the pressure, I go to liquid. I go to liquid, just from solid to liquid if I increase the pressure. Now, some of you come in this place where they have the white stuff and temperatures below freezing, and so they have lakes that freeze, essentially, and you notice the lake freezes from the top. And then the ice, obviously, is lighter than the water. Ice is not as dense as water. It floats on the water. You have observed it, isn't that right? This is because of this here. So why doesn't the lake completely freeze down all the way? That would be terrible. Wouldn't it be? Evolution every year new, because the lake would have to freeze from the bottom up, and it kills everything that's in that lake. And then every year you start with evolution, and then next year comes bang, it's gone again. You know? And so what? Now think about it. Remember when you were diving? They having the dive experiment. If you go down, you had 1 atmosphere on the surface, and then you go down to 10 meters. You have how many atmospheres? 2. So the pressure increases with depth. So if this is ice and the pressure increases, what happens to the ice? This is our temperature here. Let's see that it's 0 degree here. We have the solid, and now we increase the pressure. There you go. It becomes liquid. That way, we know, and we are lucky that our lakes and anything else is water doesn't freeze from the bottom. It freezes from the top. So as we go further down, it becomes liquid. That's a very big advantage for us. And you have here, this is the solid to the liquid that is melting. Okay, and this is the solid to, this is the solid also to the liquid. We can go this way, or we can go this way. This way we increase the temperature, and this way we increase the pressure. Both of them will come to the same result, and we call this the fusion curve here. And the vaporization curve, where the liquid goes to the gas, that's the liquid vaporization curve. And then we have here the sublimation curve, you know that, where the solid goes to the gas. That happens when you have snow on the ground, and suddenly the snow goes away a little bit because there's vapor pressure still. Okay, it's actually you have sublimation there. And so let's go back. And so you have a triple point. That triple point for water is very difficult to do. You have 0.01 degrees Celsius, and you need 0.061 thousandths of an atmosphere, okay, to get to this point. Now, what does this mean here? Critical temperature. So everything above here, it's all gas. It's all gas here. Above that point here, it's all gas. And even water behaves like what? Like an ideal gas, all right? So above the triple point, all gases behave like an ideal gas. Now, let me ask you a question. I have which plot corresponds to the process shown? What is the compound here? Water, exactly. Why do we know that? Negative slope, okay? Excellent. I'm teaching you. That's wonderful. Okay? So now this is the process here. This is the process here. So what are you doing here? Obviously, there's a temperature and a pressure, and something is going on. This is the process we are doing. And I want to know, if you do that process, which plot is correct? Is A correct, B correct, or C correct? These are pressure over volume diagrams. Pressure over volume diagrams. So which is correct? Think about it and give me your answer, please. What is the answer? Good. You should all know that. Okay. Let's do this another way. So this is the critical temperature, is that right? Are you all agreeing with me there? So what happens above the critical temperature? The gas behaves like what? Like an ideal gas. What is true for an ideal gas? What is pressure? Something is a constant. I did this many times. I derived it even to you from on a microscopic scale. You remember this guy who did these experiments, these suffocation experiments, this crazy Irishman? Okay. So why don't you discuss this with each other and show me what you got here? There's not much I can do at this point. Discuss it with each other. What is it? Of course. Yes. Good. Okay, let's get with the program again. So what we have here, we have above the critical temperature. That means it behaves like an ideal gas. That's the first thing we learned. The second thing is we increase, and I'm plotting here pressure over volume. What happens if I increase the pressure? What happens to the volume? It decreases, okay? P times V is a constant. That's this one. This would be P times V for a real gas. And this is nonsense, okay? All right? Okay, let's see if this is what I have here. Let's give you the explanation for those who really would like to visualize. It's above the critical temperature. The gas does not condense. It behaves like an ideal gas, okay? And an ideal gas, P times V equals a constant. Who was the guy who figured that out? Boyle. That was the guy who did these very important experiments, which we are now laughing about, of course, because we know that all living beings, also people, need oxygen, okay? Especially mammals. But others do. So that was the answer. So today we're going to talk about thermodynamics and the first law of thermodynamics. Thermodynamics comes from Greek. Thermo means heat, and dynamics means power. Heat power. The power of heat. All right, let's see what we can talk about there. What is a thermodynamic state? The thermodynamic state is a condition of a system, some kind of a system, usually a gas, at thermal and mechanical equilibrium. And for this to be a thermal and mechanical equilibrium, it has to have a well-defined temperature and a well-defined pressure. Okay? And this is actually a macroscopic observation. We observe that, and it's time independent. You just observe, that's the state, time independent. It's an equilibrium. So what would we call a thermodynamic process? That's a process that changes the thermodynamic state of the system. That's a thermodynamic process, okay? And so what it has to be, you have an initial state, that's an equilibrium, pressure and temperature, and then you go to another state, that's another thermodynamic state. Obviously, this is higher in energy, that state, that's why I'm pointing like this. This is an equilibrium, okay? Temperature and pressure. And you also need to be able to go without loss from one state to the other state, okay? So you go this way, go ahead, and you should be able to go back without losing energy. And so that means it's a reversible process. We call these processes reversible. You don't lose any energy. That's called a reversible process. So what is the first law of thermodynamics? When the universe was, how can I say, created? When the universe occurred, okay? When the universe occurred, so from this Big Bang, there is a certain amount of energy that the universe has. And this amount of energy will not change. You can do whatever you want. It will not change, okay? The energy of the universe is constant. So that means there's the total energy of our universe is conserved. Of course, not for us, but it's true. You will learn this, okay? So we have this funny system. We call this a system. Let's see this as a gas, okay? And we can do something on that gas. The change of energy actually is is heat and work. So you can either put heat out of the system, you could put heat in, or out of the system, something happens, or you could put work in the system, but the system does work. That's all very complex, isn't it? So, but it will get clear to you. So if the system releases heat, think I have the system here, okay? I release heat to the outside. What happens to my energy? I release heat. What happens to my energy? Huh? It goes down. Energy is directly proportional to the temperature, okay? So it goes down. Now I'm down. Now, if the outside puts heat in my system, so they're here, the room is 100 degrees, okay? Oh, it's hot, okay? So there is system, energy comes into my system, so I'm heating up. So we have this convention, when energy system releases energy, we always do this green, that's an exothermic reaction, that is minus, we have a minus sign when energy is released, exothermic, and when the system takes up energy, I didn't think about this morning, when the system takes up energy, then it's positive. So when you put energy in the system, it's positive, when the system releases energy, it's negative. That's the convention we have talked a little bit when we did about ionization energies and breaking of bonds and so on, and we will talk more about this. Okay, now, that system also could do work. I mean, this system cannot do work because I don't have a piston, but in order for a system to do work, let's see. I have a certain energy. Now I push against external pressure. Did that do work? What will happen to my internal energy? It goes down, okay? And I start eating when I put a lot of work in there because my temperature will drop, okay? So when the system does work against an external pressure, then what happens? System does work. Means the system does work. What does that mean? Let's see, that would be this here. The system does work. So that's negative. The system to the outside, it does work. So that means the temperature or the energy of the system would go down. If I, or somebody puts, behind the system, it puts work on me. Okay, what happens? I'm under pressure, okay? So what happens? What's with my temperature? It increases, okay? So my internal energy increases. The work was done on the system. That is positive, okay? My internal energy increases. So you will get the hang of this. I make this very pictorial here, as you see, but it's not a rocket science, actually. It's only thermodynamics. So the energy is a state function. So what is a state function? A state function only depends on the initial and final state. If the camera can follow me now, I'm going to go over there to the stairs, and I will show you what a state function is, okay? Am I on camera? There you go. Follow me, please. Good, but make it a little wider, the picture, that they can see me walking up this. So I have energy here. I have potential energy, okay? So now I'm going to walk up these stairs here. This is my initial state. And I'm here. I'm having higher energy now, okay? That's the final state. The difference between the two states is the energy difference. So, but I could also do the following. This is my initial state. I go up there. Doesn't matter how fast I go up there.